Are you? I think it's not this summer, but next summer there's a subduction zone.
I'm one of the organizers.
I
I'm
wrote
not.
a letter for it.
I know. Thank you. Yeah.
But
Yeah.
maybe at that
We could
like
poll people.
pull it and see if it, and then run it.
I think that's a great
Run
idea.
it like I don't know how often they think they're going to run the board conference.
It's going to be every other. We have the first year,
Okay.
and then so Jeff Abers and Kristen Morrell are like the co-chairs for the first one, and then Mark Bain and I are the co-chairs for the second one. We have to do well enough the first one to get the second one.
Maybe the second one could be that.
Well, I want it to be like fluids and definition and stuff.
Did you? So
He gave a talk on Tuesday.
what's that?
He gave the writer gave a talk. It's so worth reading.
So you want me to then email this back to you?
No, I got a box.
Yeah,
Awesome.
Marie got a bunch. Like I have one in my office, so.
Awesome.
It's.
I mean, my experience was like when ChatGPT first came out. I have this super easy writing assignment of the beginning of structural geology. Like write a paragraph about the brittle ductile transition.
And you were getting some like very.
And I told them, I really want you to write this on your own, and then I want you to use ChatGPT, and then address what you think of ChatGPT's version. And they all said, I think that I understood it better than ChatGPT did, but the writing of ChatGPT
Was better.
was much better.
That is the product, the process.
Exactly.
Is us.
Yeah. And I was like,
And that's the key distinction that I think a lot of the students like don't get, but we
Right.
gotta like.
yeah. And it's soulless.
So
Like the writing, it's like,
agents have souls nowadays.
yeah.
They're not identified. They don't have the right symptom.
Thank you, Marie.
Okay, everyone, can you hear me? Yes? Okay, we're going to get started now. It's my pleasure to introduce Greg Hirth, who's our colloquium speaker. Greg Hirth was trained as an undergrad at the University of Indiana. He got his PhD at Brown University, working with Jan Tullis. He then did a postdoc with Kolstad at Minnesota. Worked on quartz. He's worked on olivine, so the only two materials that matter in the earth. No, he knows that other materials matter, but he does know a lot about those two minerals, which is great. Greg is at Brown University now. He was at Woods Hole for a while. He's at Brown University. You're the vice provost for research there? Yes, and also a professor who does science. Greg Hirth is one of the leading voices globally in rheology and rock mechanics and rock deformation. His work has been really inspirational to generations of people doing this work, including myself. And it's been really lovely having him here, interacting with all of us. And really excited to learn more about the rheology of the interface between the mantle, wedge, and the subducting slab. Some of us know some things about this.
Yeah, I would say from what I've heard today, you guys know a lot about this, so it'll be fun. Thank you very much. And it was a really wonderful day meeting with people. Lots of inspiration. Going home, you go to these things and every idea is like, wow, that's awesome. So thanks a lot. So today I am going to talk about the interface between the mantle wedge and the subducting slab. And there's so much work going on in this area. But one thing I kind of find fun is this OG figure of seismic velocity and earthquakes from 1992 is really evocative of what's going on still. A lot's happened since then, but as an experimentalist, this is cool because there's huge variations in temperature, huge variations in strain rate, variations in composition and volatile content. So it's like a myriad number of different experimental rock deformation experiments. Maybe a little bit poorly constrained, but you know how that is. But today what I'm going to talk about is developing quartzite rheology as a rheometer, and then use that as a starting point to understand the deformation process of pressure solution and subducting sediments. And then follow up with acknowledging that there's more to the world than quartz, and understanding the importance of phyllosilicates in subduction rheology, concentrating on creep rheology of talc, which is PhD work of Hannah Shabjian, who's actually over there, wave to everyone. And this meeting actually came about because Hannah and Will Hoover and Kaylee and I are starting a collaboration of comparing the cool constraints they have from Catalina Island with the deformation experiments that Hannah's doing. So rheology always comes with a bunch of equations and mechanisms. So before I launch into that, I'll do a little bit of a tutorial to remind you or at least make it less paralyzingly complicated. So the business we're in is deformation mechanisms and flow laws. And one of the main purposes for doing this is to provide a framework for doing models of geodynamic processes. And when we do that, we don't want to just be totally empirical. So we want to understand the physical basis for the parameters that goes into those relationships. And then we have to really challenge ourselves to think about the concerns of scaling and extrapolation. So one of the things I've really concentrated over my career is comparing lab data with analyses of geologic samples. So providing a context to study a process to see if the same process is occurring and I can demonstrate that, that provides validation of using the laboratory data. And that validation is awesome. That's one of my favorite things. So let's start off with some kind of structural geology and then material science, just to give you some insight into the main processes that we'll talk about. And I'll actually talk about all of these today. So dislocation glide is the mechanism that allows the process of low temperature plasticity. So many of you have probably seen cartoons of an edge dislocation that allows deformation to occur in crystals at stresses much lower than it would require to break a plane of atoms. And you want to think of there being a diagram of the amount of work required to get the dislocation to move one lattice dimension. And that, at low temperature, requires enormous application of stress. But the higher the temperature you go, the lower that stress becomes because of the thermal vibrations. So there's an energy barrier that you have to overcome. And the higher the temperature, you get rid of more and more of that energy barrier. So the stress that you need to apply drops when you increase temperature. But there's a little bit of a weird thing in here. There's this extra bit, the internal stress. So when you put that defect into the crystal, it distorts the lattice in a way that's applying a stress against what you're trying to apply in the first place. So before anything happens, to just get to zero, really, in terms of the dislocation, you have to apply a stress. Then you have to apply even more to get it to move. And some of you might have heard of people like Lars Hansen talking about backstress and its application for understanding attenuation of seismic waves. That internal stress is the origin of that. The same is true with strain rate, right? So if you have a very low strain rate, you have a greater probability of some vibrations leading to the ability of the dislocation to move along to its next lattice position. So that process doesn't seem that complicated, but what it does lead to is an activation energy that's both dependent on temperature and stress. And that gives you this funky exponential with all this extra stuff in here. But really, that's just an explanation for that energy barrier. And then a strain rate comes from a product of how many dislocations there are, and that depends on stress, how fast the dislocations move, and how far it can move in a lattice dimension. And that's what all this junk is in here. So it looks hideous, but conceptually it's not that complicated. And this is important for phyllosilicates at low temperature, and it's also really important for rate and state friction for those of you who have heard about that. All right, so what happens when you increase temperature even more? What's cool is that energy barrier for glide goes away. It becomes essentially negligible. But then what happens is that something else has to happen to allow the deformation to occur. So this is now a 3D picture of a dislocation loop. And such a loop would originate from some source, and they propagate outwards in concentric loops to cause the deformation. And that kind of motion is also what people in geodesy use to, or in understanding slip on earthquakes. They use dislocation models, which are kind of conceptually the same as this. They're the same origin or theory. But when you have a source here, and then maybe down here there's another source, but it's over here against the wall. So this part of the loop is moving that way. These loops are moving that way. When they intersect like this, they get stuck. And the reason they get stuck is that the stresses around the dislocation line up so that a tensional stress concentration lines up with the tensional stress concentration, and that relaxes the overall stress concentration, so it's stuck there. And then what happens is material diffuses to that location, and there's a counterflux of crystalline vacancies away, and this dislocation moves down, this one moves up, and they annihilate each other. And the process can go again, that glides out and gets stuck again. So that process has an exponential temperature dependence that you'd expect, but it follows a power law. And then when you see these laws where strain rate is proportional to stress at the end, this is the kind of process they're talking about. So that would be power law creep or climb limited creep. And that's important, like in the asthenosphere or at the base of the crust, in the lithosphere. That's where that would be a dominant mechanism. And the last main process is important in myelonites, which are very fine grain size. And what happens here is that diffusive mass transfer allows material to move from orientations under high stress to orientations under lower stress. And that process is linearly dependent on stress because there's a chemical potential gradient that gets formed by that stress gradient. But it's hugely dependent on grain size. It's a cubic law. So just a factor of 2 in grain size has an enormous effect. And that will be important later on. But that's the functional form here, stress over d cubed. All right, now, that's kind of, in a class I might take 2 whole lectures talking about all that. So if you haven't heard it before and it sounds like weird stuff, that's okay. And if you have heard it before, maybe that was a different conceptual idea of it. But one of the things we're here to talk about is that we're in the lab, we're deforming pieces of rock this big in a day or a week or maybe 3 weeks. And we're extrapolating them enormous orders of magnitude in temperature or strain rate. And we have to say, is this valid? And there's uncertainties, right? You get some data and you fit them and there's some uncertainty. And there's been a misconception in the geodynamic literature that has caused people to think that these uncertainties are so big that it's really not worthwhile even doing this. And there's a really simple explanation for why that's not true, is that the uncertainty of a parameter like this Q, the activation energy, is correlated with another parameter, uncertainty in that parameter. So as a result of that, it's basically just saying your flow law has to go through the data. So when you extrapolate it a long way, the uncertainty is still there, but it's not 5 or 6 orders of magnitude. And so when you're doing a model and you want to incorporate the uncertainty, it's really, really important to incorporate that. But the most important thing is ask, is the process the same? And that is where geology comes in. And I was super fortunate when I was a graduate student. I did a bunch of stuff on quartzites, and then I went to do a postdoc at Minnesota, like Kelly said. And I got to work with Christian Tessier, who was working on rocks that deformed exactly the same way as the lab experiments I conducted. And we looked at the microstructures from high stress, low T, to low stress, high T. And they showed these variations and textures that matched really well. And they occurred in a way that really gave us confidence that the same process was occurring. So this really gave me the confidence to say, oh, this is cool. We can employ this to really understand rheology better. And we developed a flow law based on these comparisons. So some other things that give me confidence. There's a lot of discussion about what are the stress states under which faults behave. And we actually have measurements from boreholes that go down quite deep in the crust, down to 9 or 10 kilometers. And when we look at the stresses in these boreholes from various techniques, they give us an increase in stress and depth, which matches the frictional resistance in crystalline rock, following what people call Byerlee's law, down to around 9 kilometers. And when you get, this is the KTB drill hole in Germany. Just for curiosity, how many of you have heard of the KTB? So 25% of you? So what's amazing is you get down to the bottom of that thing, the temperature is about 300 degrees C, and you see that the quartz begins to behave in a way that the dislocations are moving around. And you can use the density of these dislocations, this is a micrograph from a paper by Georg Driesen, to estimate what the stress was. And when you do that, you get this red box, which is following the stress state that you measured from the borehole breakouts down to that depth. That's pretty cool, right? And then you do a bunch of other work that Whitney Baer and John Platt did, and many others have done similar work, of using the relationships like this piezometer, mainly from the grain size in quartzite, and you construct depth profiles using estimates of the geotherm and metamorphic petrology. And you see this drop in stress with depth. It looks just kind of like a cartoon of the brittle ductile transition. So that's neat. It's like giving you confidence that this concept has some basis for applying. I like this figure. I just take a little bit of time to talk about it because it's cool. That drill hole in Germany, there's another part of it that's really neat, right? They could see there's a hydrostatic pore fluid gradient all the way down to that depth. But they did more than that. They did Packer tests and measured hydraulic diffusivity in segments of the core that had fractures in different orientations. And they calculated the stress states on those in terms of a coefficient of friction. So here's shear stress versus normal stress. Here's Byerlee's law, essentially. And these dark-colored ones are the fractures that had a high hydraulic conductivity, indicating that as you're getting near fracturing conditions or critical conditions, the rock is starting to dilate. So all of these things we can do and measure in teeny little pieces of rock, and seeing these correlations at those large scale is part of the reason that you can gain some confidence that no, the Earth isn't made out of quartz, but where there is quartz, it kind of deforms the way we expect it to. And that's the main important feature there. So, here I am, 30 years into this, and my graduate student, Leif Tokel, comes in and goes, Greg, your flow law doesn't work. Look at this plot. Like, here's your flow law, and you're right, a bunch of data fit perfectly right on the flow law. But look at all of these data. This is wrong, right? All right, so I said, it's not wrong, there's just more to it. Cool. And he figured out, this was kind of a neat thing. So what he figured out was that there indeed seemed to be two flow laws that vary as a function of temperature and stress state. And not only that, when he looked at the data, all right, so just one more like lab-based thing. Just hands again. How many of you guys have looked at pole figures of anything before? All right, so a pretty good number of you. So these are pole figures of C-axes in sheared quartzites. And the ones that follow this flow law show C-axes that are coming out at you. And the ones that follow this flow law have C-axes that are up and down, indicating basal plane is horizontal. That's cool, right? And then the ones that are in between have in-between patterns. So when we go back to this paper by Whitney Bear and John Platt, and we look at the low stress or high stress, low temperature rocks that she looked at, they have the low temperature, high stress CPO. And the ones down here, at the low stress and high temperature, have the high temperature CPO. And the transition happens right where you would predict these two flow laws overlap in stress and temperature. So that's like cool. This is like second order weirdness that matches and giving us even more confidence that we can apply a quartzite rheometer. That takes us to these rocks this is from the Shimanto belt in Japan. And these are melanges that Don Fisher has looked at over the years. And the temperature of deformation of these range from like 150 to 350 degrees C. And when he looks at them, he sees evidence for a deformation process of pressure solution, which is a diffusion creep process. So they don't show evidence of dislocation creep. So you're like, all right, why aren't you going to talk about the quartz and clay and mica diffusion creep and pressure solution data? And the answer for that is it is really hard to do that because all of the tricks that we use to make things happen fast in the lab, the Earth has already done. We can't make the grain size small because the grain size is already really small. We can't go to high stress because the rocks crack, or maybe you get dislocation creep. And we can't go to high temperatures because the phase assemblage changes. So as a result of that, deformation by pressure solution has been really hard to resolve in the lab and has been based primarily on models and analogs. And just to give you an idea of the wilderness in this area, this is a plot of temperature and depth in a subduction setting. Here's depth and strain rates. And all of these bands here are different models for how pressure solution is incorporated into rheology. And it has a lot of uncertainty. And also, I mean, you're like at a given condition, your strain rate is varying by 8 orders of magnitude, depending on which parameters you use. So what we're going to do is go way down here to where pressure solution and dislocation creep intersect. And we can use our understanding of dislocation creep that I just went over to constrain the pressure solution flow law and then extrapolate that to lower temperatures. So that idea was really based, for me, that really came from this, you know, when you review papers, you're like, wow, this is a cool paper, I have to remember this. And so I was talking to Don, and he said, let's write a proposal, and we'll figure out pressure solution, and you'll do the lab experiments. So we're like, I don't know if we can do those. And so we talked and talked and talked, and there were others involved with that, including Heather Savage and Chris Marone. We wrote like 3 proposals that never got funded. But as a result of that, our story got better and better and better. So we got to write a paper about that. But this is really the start of it. This is just a really simple structure that a woman, I can't remember her last name, it might be Stephanie Kennis, and Janos Uri wrote back a decade ago. And so there are these metasedimentary rocks, siliciclastic sediments, and there's one that is a little bit stronger than the other, and there was 2 stages of deformation. One of them resulted in the formation of quartz veins in the stronger formation. Then subsequently, there was a horizontal compression that led to slaty cleavage development in the clay-rich stuff, and deformation of the quartz veins. And when they looked at the microstructures, they could see the quartz veins deformed by dislocation creep, have diagnostic microstructures of that. But the quartz in the more politic rocks did not show that, and they showed evidence for slaty cleavage and pressure solution creep. And so they ran numerical models using the type of flow laws I talked about at the beginning, but just worrying only about the stress dependence, and they pinned it to the prediction of the flow law that we had created back a while ago. So they said, there's this rheology, and then the pressure solution rheology. In order to make that shape that you saw in the previous figure, had to be over here with a linear stress dependence. So that's the foundation that we used, and we said, now we want to create a flow law because we don't want to just study rocks at 350 degrees. We want to go down to 200 degrees. And to do that, we are just going to use a pressure solution model but simplify it. So this is another mini tutorial about pressure solution and what are the important variables. This goes back to a paper by Farr and Ashby in the 80s. All the grad students remember to look at papers from 50 years ago. They did experiments on KCl, so salt, and they did experiments with water present, dry, and with kerosene as a pore fluid. The dry ones and the kerosene have this hideous low temperature plasticity flow law, but when they added water, the stress exponent became 1, and if I extrapolate this down here, this is like, 7 orders of magnitude difference. The water, it totally ripped. It went super fast. So this is evidence of a pressure solution, and they further documented that by showing that the strain rate at a given stress increases when you increase the solubility in the fluid. And they did that. They didn't use kerosene for that. They used alcohol. So they varied the solubility by changing the amount of alcohol in the sample. That was really cool and insightful. And people would love to be able to do this in quartz. No one really has ever done it. Someone might. All right. So what we then did was note, the important bit here is the solubility in the flow law and the diffusivity of silica in the fluid. And there's other geometrical terms that are a nightmare to figure out. They could be stress dependent. So we're like, forget that. Just go back to Kenes and put the things that we know in the flow law and apply it, and just lump all the stuff we don't know into some constant in front. That make sense? So when we did that, now we want to apply it to the subduction setting. So we go back to plots like this. And so there's a couple important things here. The first one is, on this plot, these are the flow laws for the pressure solution law at grain sizes from 5 to 20 microns. And this is the dislocation creep flow law for a strain rate of 10 to the minus 12 per second. Give you an idea, 10 to the minus 12 per second would be plate rate on around a 300 meter wide zone of deformation, of sediment, underplated sediment. So what's the friction coefficient? On here I say the mu prime is 0.04. That's not Byerly's law. But this coefficient of friction doesn't include anything about pore fluid pressure. So 0.04 is consistent with Byerly's law, if you like, with a pore fluid pressure that's 95% of the lithostatic pressure. So really high pore fluid pressure. And the origin of this 0.04 comes from a lot of work on places like Cascadia of how weak does that interface have to be on a tectonic time frame in order to see the temperature structure we see, the lack of heat flow, and the lack of geoid anomalies and all kinds of things like that. The plot on the right is where we start to see things that we can test. So here is a line 10 to the minus 12, so we call that no slip deficit. That meaning you can just accommodate all the plate rate by this deformation mechanism. And this line here is where you would actually see evidence of visible strain. So what's visible strain? That's roughly, like you can see with your eye something like 5 to 10% strain. You could tell that the rock was deformed. And what's really neat is that we can get down to the condition of where that Kenes paper was, which is here. So the pressure solution for the grain sizes that you would predict down here, so in the range of 10 microns, is greater than that for dislocation creep, just as you would predict. But what's really important is that you see evidence of visible strain all the way down to like 200 degrees. We know the rocks are deformed because we can see those mechanisms. It's just at a rate, orders of magnitude too low to accommodate the plate rate. So there's a number of things that were cool when we apply that. The depth where you expect to see some visible strain matches where you start to see scaly fabric developing in the sediments. The scaly fabric is like slaty cleavage for shear. It's evidence of pressure solution. And the depth where at the base of the seismogenic zone matches where those mechanisms are fast enough to accommodate the plate rate. There's a million things we're not accounting for, but on a gross scale, it accounts for a lot of observations. One thing that's important, it takes like 1 to 3 million years to traverse this distance. So even though the strain rate is really small relative to what you need for the plate, if it does that whole thing over 1 to 3 million years, you can accommodate, get up to shear strains of like 100%. And you see some of these melanges clearly have strains that are pretty big. So that's cool. Remember, though, there's been thousands of earthquakes over that interval, big ones. So it's amazing that we can see these textures, but it would be hard to identify any single event within this stuff, although Kaylee's group is doing a great job, and Harold as well is trying to understand that. But the correspondence we see between these mechanisms, like, let's be bold and see if we can compare it to geodetic data. So the last bit here is to say, if we look at the geodetic data for where we're standing, and look at estimates for the slip rate deficit as a function of depth, you get something like this, where it's locked up here, and then you start to see deviations from that down to around, getting down to like 0 at around a distance from the trench of about 200 kilometers. So where the temperature is getting around 400 degrees. These lines that you can see magically going through the data, kind of crossing those lines, are the pressure solution flow law with variations in the width of the sediment and the grain size. And to give you an idea of how well we know the grain size, it's hard, but we know the grain size of pelagic sediments. You know, the grain size is like 1 micron. And we know the grain size in the higher grade rocks gets up to be around 20 microns. So that range is pretty well documented, and how it evolves is pretty cool. But the really interesting is that you can see that this flow law does a good job of matching this large-scale tectonic story. Now, why do I like that? What do we not understand at all? Well, that's not fair. What do we still stink at trying to explain in a way everyone believes? What are the mechanisms of things like slow slip events and tremor? What causes the nucleation of a big earthquake? What are the rate and state properties that do that? And the stress state under which that's happening, right? So those are all the questions that you can use a framework like that to at least say, well, somewhere we think this is what the stress state is. And that seems to match some large-scale geodynamic system, which is at a time scale much longer than any of that's happening. All right, so let's talk about that rheometer one more time. Maybe another time later on, but one time now. So in the Makamani melange at temperatures near 350, which is the condition of where we started from, you see something cool. You see Boudined quartz veins with microstructures that are indicative of dislocation creep. And they have the pole figures indicative of this boundary region between the two flow laws we talked about before. And when you look at the quartz in the metapelite, you don't see that fabric. It's maybe a little teeny bit of one, but not really. And it's clear that the pelite is deforming much faster. So the stress state you get from the grain size analysis here is around 20 MPa, so somewhere kind of in the ballpark of where we're thinking this is going to happen. And if we go onto this plot at 350, we see, so the grain size in the metapeolite is like as small as 7 and as large as 20. So in this range, and it's deforming faster than the dislocation creep, which it's Boudin, and so it's consistent. So the rocks from the Shimanto belt show this transition that matched where we started from. One more thing. The stress state, we're talking about 20, 30 MPa shear stress. That's a lot bigger than people might guess based on what types of phenomenon lead to the triggering of slow slip events, which are like, and that happens. All right. So how well do we know the stress state? And I, as like a scientist who's been around for a while, I have some like icons that subducting interface is weak, and 2 of them come from right from this area. And 2 of them are presented in a paper by Kellen Wong from 30 years ago. It's like a long time ago. Is that 30 years ago? Yeah, 30 years ago. One of them is that if you look at the moment tensors of the upper plate earthquakes, that they show T-axes that make a girdle, and that the principal stress direction is actually kind of parallel to the trench. The maximum stress is parallel to the trench. So that gives you a stress state where sigma 2 and sigma 3 are almost the same, and that's the stress state that the subduction interface is operating on. So that's kind of neat. And then consistent with that is the heat flow story that probably a lot of you are familiar with. I don't know how much this story's evolved in the last 30 years, but my understanding that the resolution is a little wiggly, but still you have to have low coefficient of friction in order to explain the heat flow. So that's kind of a large scale thing that suggests that the stresses are low, but if you look at other indications of stress, like stress drops, how many of you know that stress drops seem to be nominally independent of depth, right? And independent of magnitude. Ish. All right. But everyone's always looking at that in like some 15-kilometer deep seismogenic zone. What if we go to a cold subduction zone where the brittle ductile transition is at 60 kilometers and look at earthquakes there? And this is a paper by Uchide and Shearer and others. And here you see this amazing thing that the corner frequency-based stress drop increases with depth, up to values of like 100 MPa at 80 kilometers. So now why is that important? It's important for 2 things. One is those estimates are kind of similar to what you predict from this coefficient of friction of 0.04, right? If I extrapolate that down here, this is where like the magnitude 4.5 earthquake stress drops are. It's kind of pretty consistent with that. That's pretty cool. But what does that do? By going deeper, the stress is higher. So we can make the strain rate of all of these processes faster at a given temperature because the stress is higher. And as a result of that, one thing that's cool, there are other things, but one thing that's cool is like a 10 micron pressure solution law can accommodate plate rate at a temperature of like 200 degrees, if you just believe the flow law. And even more incredible is that you can get the strain rate for after slip all the way down at 50 kilometers. And one of the things that's amazing about the Tehuco region was after the earthquake, in the year following the earthquake, there's this region of after slip that shows like 3 meters of slip. So something happened to allow 3 meters of creep to happen over a year. And that pressure solution flow law, you can't really rule out as a mechanism that's viable for that, which is kind of cool. But why was that possible? It was only possible because it's so cold that you can get to higher stresses by having to go so deep. All right, now Hannah gets to be the star of the show. So talc, everyone knows talc is weak. But one of the other weird things about talc is all the experiments that have been done on it have shown brittle deformation. And no one had ever really tried to deform talc at high pressures before. And high, I mean like a gigapascal or 2 gigapascals. The one reason that's probably true is that the stress resolution in the rigs that you would do that stank, and it was like, I don't know if I'm even measuring anything. So I think probably that was part of the reason. But as you guys probably know, that talc is a fascinating mineral that shows up in important places for geodynamics and is called on as an important mechanism to accommodate the decoupling of the downgoing plate, and is present in areas where there might be slow slip events as well. So this story really begins with a former student of mine, Eric Burdett, who was a kind of a whiz in the lab. He still is a whiz in the lab. But he developed some techniques to decrease the frictional in the properties of the rig so you could isolate the properties of the rock. And we started doing what are called creep tests, which, just to give you a quick idea about that, you apply a load and then measure the creep rate instead of applying a displacement rate and measuring the stress. And so the work he did gave us confidence that we knew what we were doing. And with that type of technique, you can acquire a lot of data at very, very low strain rates in the range of 10 to the minus 8, because you get the steady state in a really small amount of strain. That's a really important part of that. And so he did this in antigerite and found this really beautiful data set that shows the hallmark of low temperature plasticity in serpentine. Hannah came into the lab just at that time and started doing, her experiments were designed to study pressure solution. But what did we find? We found low temperature plasticity in talc. And so she concentrated on that and found really good evidence for the low temperature plasticity in talc. But I want to emphasize some aspects of her data that are really important. The coefficient of talc is really low. It's like 0.1. So if you go up to a gigapascal, the stress you need for frictional slip is in the range of like 100 to 140 megapascals of shear stress. And all of her data at that point clump up into one kind of cloud. And there's evidence that that is probably frictional, and there's not a strong temperature dependence to the friction at that point. But by able to go to low stresses, she sees this really systematic temperature dependence. It's an indication of low temperature plasticity. And you couldn't get these data at low pressures because the friction coefficient is so low. The shear stress is only 10 megapascals. At 700 degrees, her highest temperature, the strain rate is 3 orders of magnitude less than the frictional strain rate that you're applying. So it's like the technology in the lab, despite doing these experiments for 50 years, new things keep coming on, and you can apply them and get new data, which is really cool. So let's compare talc to serpentine. Talc, at say 50 megapascals and 500 degrees, you're talking effective viscosities that are orders of magnitude lower than serpentine. So where it is present, it could really, really be important. And to give you some context of that, Hannah makes this plot of shear zone thickness needed to accommodate plate motion as a function of temperature. So at 500 degrees C, in a stress range in this region, if you just have in a package of rock that's kilometers and kilometers wide, if you have an accumulation of 10 meters of talc, you have 100 centimeter thick or whatever the math is. And maybe you need 1,000 centimeter thick shear zones. Is that right? Am I doing that right? 1 meter has 100, right? So 10 meter has 1,000. You need 1,000 of them. You could accommodate all of the platelet with that. And you can even go, if you as an example, what's the widest talc zone that you've seen? Yeah. So if you had 5 meters, which is a lot, I'm sure that this is going to happen, but if you had 5 meters, this flow law would allow you to get to slow slip rates. So while it's a viable thing to think about, it's clearly geodynamically important. And some other work that Hannah is doing that indicates that as you get near the transition to where talc starts to dehydrate, you pump up another couple of order of magnitude decrease in viscosity. But it was really important for us to do these tests because it shows us why, we know talc was weak, but now we can quantify it. And one of the reasons that we are here is to see if we can test these laws with the rocks that Kaylee's group has been collecting over the last few years. And we had a lot of fun talking about this at a Gordon conference and then over Zoom. But it wasn't until we could just sit together for a couple hours with the microscope and the rocks and discuss this. And you're like, all right, now we have a story. And so that's cool. That's one of the fun things about doing these strips. All right. So I'm going to wrap that up. So what did I talk about? So in reverse order, as no one is too surprised about, talc has a really, really low effective viscosity, and it can be really important geodynamically. Talc isn't just important in subduction zones. There are clear evidence of talc tremolite schists on the detachment faults, on normal faults in the oceanic spreading centers. Transform faults have a region where talc is stable, and you observe talc in the gouge from the Cephod drill core. So there's lots and lots of applications for this beyond just the subduction setting. It makes us think more about what are the processes that could conceivably accommodate slow slip rates. And I would point right back at me about what about the stress state. But the work that we did with Dawn on pressure solution suggests pretty good evidence that the stresses down in the 30, 40 kilometer range could easily be 20 megapascals, consistent with the microstructures you see in the rocks. And that was based on taking a real deep dive into quartzite rheology, where we really can understand the microstructures that form, match them up with what we see in the lab. Quartz has maybe the widest variety of deformation microstructures of any mineral. I'm going to still vote for that. And that kind of unique thing gives us more confidence in the extrapolation of those data. And so that's kind of my beginning to end of flow laws are awesome. They're great to incorporate into models. Do so with care. Care about rocks because they're key to understanding that. And then make sure that you compare your data independently with geophysical stuff. So thanks a lot.
Thanks, Greg. We have time for questions. I'll start.
Good.
Okay. So, right, you're talking about this stress state or change in stress drops, right, that can trigger slow slip events. So how do you square that with this switch between pressure solution or talc, or right? We're going from we're changing a couple kilopascals with tidal forces, and we're changing strain rates orders of magnitude. So how does that work with low temperature plasticity, pressure solution in your mind?
Yeah, that's really important because those stress changes won't do basically anything to your flow law. So what the picture that I try to develop is that you have some patch that has these weak materials in it, but it has to be blocked by something, right? Maybe there's a step over that's not talc, or maybe the patch of talc is not interconnected and there's stuff in between that really has to form. there are a lot of things at those conditions that are brittle, and I'm guessing that the triggering involves the processes that break those things. So where's the, like, wait a second, Greg. There's some work by Noelle Bartolo where she's looking carefully at where the slip is and where the evidence of say, tremor is. And it argues that maybe that story doesn't really add up. But then in conversations I have with people about a wide variety of people, there's clearly more that we don't really understand than that we do understand. So I would still stick with that as a working hypothesis of how you could do it.
So, like, you think the tremor patches are basically your way of bridging between these weak materials that
That's
are
right.
slowly slipping?
That's my guess.
What do
But
you think?
that's if you have to have the stress like at 20 MPa.
Yeah.
That's how you can have such a small stress do something that allows it to go.
Yeah. Okay. Questions? Joan?
Yeah. Uh-huh.
So when you do the experiment, you have to count somehow for that evolution to the point at which they begin. So you've assumed certain
Yeah,
starting conditions.
definitely.
How does that?
Yeah, that's a great question. So the flow law has in it the parameters that you impose on the lab experiment. The Earth does something different, right? There has to be some initial condition, and that initial condition for the stuff we were talking about was pelagic sediment, right? Like the clay with teeny little quartz particles, where the clay particles are like 1 micron big. And so then that rock, as it goes down, it gets squeezed and water comes out. And then it starts to go through diagenesis, and that is a pressure solution process. And so when you look at the rocks that got up to around 200 degrees C, you can see the grain size is clearly larger. So through diagenesis, it's starting to grow. But your point is really important. What happens when there's hundreds and thousands of magnitude 7 earthquakes? They're probably cracked a lot. And you see evidence of that in the rocks. They show clear evidence of some brittle deformation, but they also show clear evidence of the pressure solution process. The rocks that I was showing you are not they're probably rocks that are adjacent to where the slip on the major earthquakes is happening, but there's no way that the brittle deformation processes weren't affecting the rock. So how do you deal with that? The only way you can really deal with that is use the kind of tools that Kaylee uses, and Anna's somewhere in here, of like looking at the scaly fabrics, or what, in the old days you might call a slaty cleavage, for people who remember about that from fold and thrust belts. And then say, well, how does the brittle deformation affect that? How am I recycling the grain size? And so you would want to have a model for that, but we don't really understand that well enough to do anything other than, well, let's put a variation in grain size in the seismic cycle, and what does that do in a model? But you'd want to test that with rocks, and that's really the key part of the geology in this story. But what I was compelled by was when you look at the rock and you can see evidence of this process, but at a rate that's too slow to accommodate plate rate, at a rate big enough that you see evidence for it, and that's what the rocks show, then I say, well, you should account for that in models. So that if the rocks follow what these flow laws are telling you should happen, that's kind of an initial condition that you might want to set up a model, but that would be not a million, maybe 100,000 year time frame of initial condition that you'd want to start rocking with earthquakes and looking at what the effect of the earthquake was on the behavior. But you'd have to have a model for that. So in the lab, I mean, just riffing, what would I do? Well, I would take a rock that's kind of deforming in that mechanism, and then I would do something like hit it with a hammer. It's like crank on it with a really high stress, get it to crack, and then let it relax and creep again. And do that 100 times, right, in a really short amount of time. What did that do, right? So we've done some things like that, but not tons. Other people have done work like that. So does that help a little bit? Yeah.
Thank you. There's a lot to think about in here, and I think I'm taking away that pressure solution. You're recognizing the pressure solution is important in the subduction environment. Mm-hmm. You mentioned cleavage, and that implies to me volume loss. There's material being dissolved away and taken out of those rocks.
Yeah.
How does the change in volume play into these processes? What do you imagine?
Yeah, that's a great question. So there was work like that done back in the 70s, really, where people started understanding that people understood pressure solution a long time before that. People could empirically look at rocks and say, oh, look, the crinoid is dissolved, right? So people had this idea isn't new. It's, I don't know if it's a century. It probably is. If I knew my history better, there's probably evidence of pressure solution from 1890 or something. But in the 70s, people started applying techniques to look at exactly that problem, right? Of P and Q zones in slate belts where there's quartz veins and slaty cleavage formage. And people started looking at isotopic ratios of like, does the vein have the same isotopic ratio as the rock before it? And you could see there's some scale where the system might be relatively closed, but at the scale of the cleavage in the veins, it obviously is not, right? And one of the cool things is the veins and the cleavage help accommodate deformation. That's part of the process. And so important question there is, what's the link scale that's important? And that's where the link scale is probably still the grain scale. But I think that's an open question. I would ask, that's an important one. Is that clear enough? Yeah. Cool. Yeah.
Thanks for that. Yeah, it was nice to see those explanations. Dislocation will So, yeah, whenever I think of pressure solution, I think of rocks that are really wet.
Yeah.
I think that's not quite the way to think about it. But I'm just curious, and you kind of touched on this early on in one of the talks you showed, but what is the minimum amount of fluid content in your rock to get pressure solution at rates fast enough?
Yeah, I don't think we know the answer to that, but the key part of the pressure solution law is that it has a fluid phase present, because you need the rapid diffusion in that fluid to get it to work. Without that, then you just move back into what we would call diffusion creep, where it's like the diffusion along a quartz-quartz boundary or quartz-mica boundary that's important. So when we study like a feldspar myelinite, we're not thinking of it as pressure solution. We're thinking of it as that type of process. But the key to pressure solution is that process is clearly faster when you have the fluid present. And then you see that, remember in the salt experiments, you see the effect of solubility that ties directly into the flow law. Yeah. So fluid presence would be the requirement. And if you follow this literature, it gets ugly. And that's not fair. There's a paper that's really great by, oh man, what's his name? French guy, super nice. Sometimes names escape you. it's like a review paper on pressure solution. It's 120 pages long. And it is thick, right? Because there's all kinds of fascinating things like electrochemical potential and what's the difference between a mica quartz boundary and a quartz boundary. And then there's really awesome work done by Brian Evans and Steve Hickman, where they looked at just a single crystal of salt and clay and whether it would move closer if you applied a stress. And they measured this with really like interferometry under a microscope. It's like super well constrained things. So you can see evidence that the clay is really critical for pressure solution. And maybe that weirdness of clay allows the properties of the fluid to behave in a way that pressure solution works at all. And that's why, remember in the beginning, I talked about all the variations and the flow laws for pressure solution. People know those things, and then they make a law that incorporates them. But we don't really know all the variables involved with that and how they change when you go to a long time frame, right? And so that was, to me, it was frustrating. Like, I understand a dislocation, and I understand the dislocation density, and I even understand why when I add water to a crystal, that diffusion happens more rapidly, so climb can go faster, so it creeps faster. All that makes sense. But the pressure solution stuff, I'm like, I don't even know what this really means. And then people will automatically make it more complicated. And why? Because they need to explain something. But if we take it from the other way around and say, well, the one thing that everyone pretty much agrees on is that if the process is limited by diffusion in a fluid, the solubility is important and the diffusivity is important. And if I just use that and the observations of rocks, that gives a flow law that kind of makes sense. But I would say it motivates us to think about what you asked even more. Like, okay, how can you make this work? Yeah. Long answer. Sorry. Yeah. Yeah.
I guess thanks for the talk. I guess kind of follow up on that is, I guess if I'm trying to, I don't really think on like this like scale of topic, but if you're trying to like translate up,
Yeah.
maybe like a subduction environment,
Mm-hmm.
large scale
It is, yeah.
area, you're trying, I guess like there's a couple different flow laws that describe different systems.
Yep.
Are they applied to large enough pieces of that system where you could potentially figure out with like different kinds of buffers of your visible observation?
That's a great question. Yeah. Yeah, that's a great question.
Part of your zone is which
Yeah, there's some. Can I answer this in like 2 minutes?
You can do it in 2 minutes.
Okay. So what you'd want to look for is what process are you going to be looking for? So a seismic image is you're going to be limited in that because you're going to be talking, I don't know, what's the best resolution you can envision? Maybe is from like a receiver function bounce point is going to give you something that's in the range of 100 meters wide or something. But you can create like a VP-VS ratio, which people use to identify the presence of fluid. That VP-VS ratio can also be created by a foliated phyllosilicate rock, right? So one of the things you could say is, well, if we think this process is important in a 300 wide zone that has foliated phyllosilicates in it, does the seismic structure match that prediction? And I think the answer to that is possibly. But there's obvious evidence of fluids, too. Like, you have to be an idiot to say, oh, fluids aren't important, right? There's no way that's not true, right? So that's one way of looking at it. And so the approach that I like to take is it's already an enormous change to go from something this big to this room, right? So if I can match the process from like teeny sample to the outcrop, I've gone most of the way there almost. It's a huge step. So then the last minute of that 2-minute answer is how do we do that in other places? The best place by far is looking at seismic anisotropy in the mantle. is where we understand that all this, when Kaylee said, we understand quartz and olivine. We know more about olivine than quartz. And you can predict aspects of the seismic anisotropy and how it varies as a function of shear strain and depth and things like that really well in the oceanic mantle. So that is over 100 kilometers where it works. So it does work, but you can only make it work if the observations can measure the scale that you're interested in. Glaciers is another one, actually, right? Except for dirty ice, right? All right, that sounds like enough, right?
Yeah. Well, and it's never enough, but I think it has to be enough for now. Okay, let's thank Greg one more time. And see you all later. Remember when we learned about Rheology?
Yeah, exactly. All right.